Today we'll be talking about phase diagrams. A phase diagram is a graph of pressure versus temperature for some substance. So I have a couple examples in your book, page 469. I'll show you some more examples after this one as well. Just want to point some things out on this graph. Pressure could be in whatever units, temperature, same thing. Usually it's Celsius, and pressure usually in torr or atmospheres. So we have three lines. So on this one, this is labeled line A. This is line B. It's kind of tracing those over so you can see. And then this is line C. I know not really lines, are kind of curves, but that's fine. So let's skip ahead just a little bit in the notes. Something that you need to be able to recognize is where, at what pressure, what temperature, substance is a solid, a liquid, and a gas. So let's label those on here. So at really low temperature, so we're on the left side of this diagram, a substance is likely to exist as a solid. Conversely, at really high temperature, so over here, a substance is likely to exist as a gas. So left of the A line, left of the B line, solid, right side of the C line, gas, and then in between B and C, the substance is a liquid. So it's always going to be like that. Lowest temperature, solid, highest temperature, gas, in between, liquid. Now this line A is the equilibrium line between solid and gas. So on all of these different points on here represents the pressures and temperatures at which the substance is both a solid and a gas at the same time. Likewise, this line B here, this line represents all the points, all the pressures and temperatures where the substance is both a solid and a liquid simultaneously. So we call that an equilibrium line. And then this line C here represents all the different temperatures and pressures at which that substance is a liquid and a gas. Not only do these curves or lines represent equilibrium between two states of matter, let's take line C, for example. This also represents all the different boiling points of this substance. Remember, boiling point of a substance depends on pressure. So if you were to increase the pressure, the temperature at which boiling occurs will increase as well. This here, line B, is the line showing all the different melting points for the substance. So melting point, like boiling point, changes with pressure. And then here, between, or line A, we have solid and gas. So this is the different pressures at which a substance sublimes. Different pressures which correspond to different temperatures. So if each line represents the equilibrium between two states of matter, what about point D here, where all three of these lines intersect? This is known as the triple point, and this is where the substance exists in all three states of matter. So we'll look at water's triple point in just a bit, but that's what letter D represents. All right, if you didn't get a chance to fill in some blanks, here they are. We're going to skip ahead to number 6, the significance of the slope of the solid liquid line. So that's on this graph, that is line B, the equilibrium line between solid and liquid. And so the slope of this line will tell us about the state of matter that is the most dense for that substance. Now, something to keep in mind, a substance will exist in its most dense state of matter at high pressure. So if you increase the pressure on a substance, push those particles together as much as you can, it's going to lead to the most dense state of matter. So here's how it works. If the slope of the solid liquid line is negative, that means that the liquid phase is more dense than the solid phase. Now, the only substance that comes to mind that is more dense as a liquid than as a solid is water. Pretty much every other substance on Earth is more dense as a solid than as a liquid. So for most substances in their phase diagram, the slope of the solid liquid line will be positive, indicating that the solid is more dense. Let me show you what I mean here. So we'll take a look at a couple phase diagrams. Of course, on the left, this is for water. I mentioned I would go back to the triple point. Look at the triple point for water. So at what temperature, what pressure does water exist simultaneously as a solid, a liquid, and a gas? Just above the freezing point. So here's the freezing point for water. So just barely above, I don't know if this is to scale, but that's 0.01 degrees Celsius. More striking than that is look at the pressure. So it takes a really, really, really low pressure to have all three states of matter present at the same time. So we're right here at sea level, about 101 kilopascals. So to get the triple point of water, 0.6 kilopascals, not even 1 kilopascal. So 100 times less pressure than what we experience normally. All right, so let's go back to slope of this solid liquid line. So again, for water, the slope is negative. So let's say you're right here. I'm gonna make this darker. So let's go to black so you can see better. So let's say you're right here. So we have some water at negative, I don't know, negative 2 degrees Celsius, 1 atmosphere pressure. Question for you: how do you melt a solid? Go ahead and pause the video and answer that question. All right, so what's the regular way we melt a solid? We can increase the temperature. So if we go here, so moving right across horizontally, we go from solid to liquid. So as we can see here, crossing that solid liquid line, that is the process of melting if you're going left to right, freezing if you're going right to left. So one way that we can melt ice is by increasing its temperature. Now there's another way. Let's see if you figure this out. There's another way of melting ice. We can melt ice by increasing the pressure. Do you know that? If you increase the pressure on ice, you can cause it to melt. In fact, this is how ice skates work. You got this really thin blade. You're applying a lot of pressure, a lot of force to the ice. And if you apply enough pressure, you can cause the ice to melt. So it'll be a liquid water right underneath the skate, and then the skate can move rather frictionlessly. I know my line's not perfectly vertical here, but hopefully you get the idea. Something I did not mention earlier as well is normal boiling point and normal melting point or freezing point. So 1 atmosphere of pressure, so whatever that temperature is, that's the normal boiling point. So at 1 atmosphere, the liquid gas line. And then right here, you kind of can't see my line, but at 1 atmosphere where we hit the solid liquid line, that is the normal freezing or normal melting point. So let's go back to this phase diagram. And again, some things to mention here. We have this represents all the different melting points or freezing points. This represents all the different boiling points. So again, crossing the liquid gas line left to right, that is boiling. Right to left, that is condensing. So let's say we were, I don't know, let's go with right here for this substance. Actually, no, let's do it the same way that we did. Yeah, that's fine. We'll do it this way. So at this point, we have liquid. So whatever this pressure is, and whatever that temperature is, this substance exists as a liquid. Question for you is how do you turn a liquid into a solid? Pause and think about that. Well, you can turn a liquid into a solid 2 ways. One, you can decrease the temperature. So we see that here. If you decrease the temperature enough, that liquid will turn into a solid. The other way of turning a liquid into a solid is by increasing the pressure. Obviously, this doesn't work for water, but for every other substance, if you increase the pressure of a liquid enough, you can cause it to form a solid. Oh, I didn't mention this down here. So this line here, from left to right, is the process of sublimation. You're going from a solid directly to a gas. The opposite of that, going from a gas to a solid, that process is called deposition. up, let's talk about critical phenomena. It says if a liquid is heated in a closed container, its vapor pressure will continue to rise until the density of the liquid equals the density of the vapor. Interesting how this happens. At that point, the boundary between liquid and gas phases disappear and the entire sample behaves as what is called a supercritical fluid. I can see some diagrams of this on page 469 in the middle, and we see at some point where liquid and gas phases look to be the same, and this is known as a supercritical fluid. The point at which the above occurs is referred to as the critical point. So we saw that on the phase diagrams here. So here's the critical point. Let's show that in a different color. Critical point for water, and then this is just some generic substance, critical point for that substance. Critical point is a temperature and a pressure. So the critical temperature is the temperature at which the above occurs. Critical pressure is the pressure at which the above occurs. So here's the thing. You get to points where, and then for water, that happens to be 374 degrees Celsius. You get to a point where no matter how much pressure you apply, you cannot have a liquid, really, is what a supercritical fluid is. What's kind of a liquid is kind of a gas. And so the particles are moving so fast that no matter how much pressure you apply, you can't cause them really to stick together. So notice for water, the critical pressure, 22,000 kilopascals. So that is really high. It takes a lot of pressure to hold those particles together if they're moving so fast. So we have critical pressure, critical temperature for water is listed there. Not super important, but wanted to mention that nonetheless, since they were given to you on both of these graphs. All right, that concludes this lesson. We have one more to finish up the unit, types of crystalline solids, and we'll cover that next time. Thanks for watching.